everybody. In this video, we're going to be talking about the mathematics of standing waves. Standing waves, as we discovered in DL today, are just waves that aren't traveling in a direction. They're just standing in one place and oscillating up and down. These waves tend to occur in scenarios where the wavelengths of a wave are restricted. For example, if you have a string that is tied down at both ends, then the only waves that are allowed on the string are waves where there is a node at both ends of the string. Let's see how we can use this information to determine what the wavelengths of the waves are. Suppose I have a string of length L. This string is tied down at both ends, meaning there must be a node here and a node here. Let's see if we can figure out what the allowed wavelengths for a standing wave on this string are. To do that, I'm going to draw a few waves that satisfy this requirement. Then we're going to see if we can figure out a pattern between the wavelengths of these individual waves. This first wave is known as the fundamental mode of the string. It's the longest wavelength that can still have a node at both ends. What is the wavelength of this wave? Well, looking at it, this appears to be exactly half of a wave. It's just a peak. It's missing the trough. So if this string is of length L, and this wave is fitting half of itself on that string, then the wavelength of this wave is 2L. What about this wave here? Well, this looks to me like a complete wave. It involves a crest and a trough, and it starts and ends at a node. So this is one full wave. And if it's one full wave, and it's on a string of length L, then its wavelength must be L. Let's look at one more wave. I think this will be enough for us to start to see the pattern. How much of a wave do we have here? Well, we definitely have one complete wave. We have a peak followed by a trough, but then we have a second peak. So how much of a wave is this second peak? Well, we know how much just a peak of a wave is because we've already thought about it here. It's just half of a wavelength. So this wave here is fitting 1.5 wavelengths on a string. So if we have 1.5 wavelengths on the string, what is the wavelength of the wave? The easiest way to do this is just to write it out. As we said, 3/2 of a wave is equal to the length of the string. If we want to then solve for the wavelength, we just divide by 3/2. So the wavelength of this wave is 2/3 L. Now you may be looking at this and not seeing a pattern. That's fine. I'm going to rewrite these numbers slightly to help us see that pattern. So this wave has wavelength 2L divided by 1. This wave has wavelength 2L divided by 2. And this wave has wavelength 2L divided by 3. Can you guess what the wavelength of the next wave would be? If you said 2L divided by 4, you're absolutely right. This pattern will continue. Let's write this out in a general mathematical form. This equation gives the allowed wavelengths for a wave on a string with both ends tied down. Or, for example, a tube with both ends closed. N is just an integer. An integer is just a counting number, 1, 2, 3, 4, 5, etc. Any value of n that you plug in here will give you a wavelength that will fit on this string with a node at both ends. Now let's consider the case of a string with one end fixed and the other end free to move around. The fixed end always has to be an antinode, while the free end always has to be a node. What is the longest possible wave that we could fit on such a string? Well, it just looks like this. Now, you might not look at that and think of it as a wave, but it is a piece of a much larger wave. If we were to draw the whole wave out, it would look like this. So what fraction of this wave is this piece? Well, it looks to me like this piece is just from here to here, from the first node of the wave to the first antinode of the wave. This is just 1/4 of a wavelength. So if the length of this string is just 1/4 of a wavelength of this wave, then the wavelength itself is 4 times the length of the string. Now let's see what the next wavelength is that fits on this string. As before, this wave has a node at the end that's fixed and an antinode at the end that is loose. How much of a wave is this? Well, we have a peak, which is half of a wave, followed by the first half of a trough, which is 1/4 of a wave. So there are 3/4 of a wave on this string. This means that the wavelength of this wave is 4/3 the length of the string. Let's do one more to get the pattern. How much of a wave do we have here? Well, we have one peak and one trough, which is of course one full wave. But then we have this additional half of a peak. As before, this half of a peak is just 1/4 of a wavelength. So we have 5/4 of a wavelength on this string, which means the wavelength itself is just 4/5 the length of the string. Can you start to see the pattern here? Let's use the same trick we used for the first case. So the first wavelength is 4L divided by 1. The second wavelength is 4L divided by 3. And the third wavelength is 4L divided by 5. Can you figure out what the next wavelength would be? If you said 4L divided by 7, you're absolutely right. Just as before, we can write out a mathematical expression that represents all of these waves. It looks like this. As before, n is just an integer, a counting number. For example, if we plug n equals 1 in here, we get 4L divided by 1, which is of course the wavelength of our first wave. Plugging in 2 gives us 4L divided by 3, and so on. When doing standing waves, it's important to know which kind you're using. Now you may notice that we haven't done the case where both ends are free. We've only done both fixed, or one end fixed and one end free. It turns out that both ends free behaves the same way as both ends fixed, at least as far as the wavelength is concerned. Now let's talk about an application of standing waves that you probably had never heard of before this class. This next portion of the class deals with quantum mechanics. You could spend an entire career studying quantum mechanics, so we're not going to get into the nitty-gritty details here. However, one of the things that we do need to know about quantum mechanics is that it predicts that particles have wave-like properties. You may have heard that light can be both a wave and a particle depending on the circumstance. It turns out that particles themselves, such as electrons, protons, etc., also behave this way. They have both particle-like and wave-like properties. While it may be nice to think about electrons as little billiard balls flying around, their behavior is actually a lot more subtle. Let's see briefly what one of the consequences of these wave-like properties is. One of the classic problems in quantum mechanics is known as the particle in a box. Imagine that we have an electron. We've confined it to a very, very small space, a space that is small even with respect to the size of the electron. Because the electron behaves like a wave, if you put it in this box, it's going to behave sort of like a standing wave on a string where both ends are fixed. The reason that both ends have to be fixed is that the particle is not allowed to leave this box. And so the probability that it finds itself at either of the edges is 0. This corresponds to a node in the particle's wave. Let's derive one of the first consequences of this. Since we know the particle behaves like a standing wave on a string with both ends fixed, we can use our result from that example in order to figure out properties of this electron. We know that a standing wave on a string with both ends fixed is going to have this wavelength. So the particle will also have this wavelength, 2L divided by n. There's another result from quantum mechanics that's interesting here. The wavelength of a particle turns out to depend on its momentum. This relationship was worked out by Louis de Broglie in the first half of the 20th century. It just says this: the wavelength of a particle is just equal to h, which is a constant, divided by its momentum, p. H is just Planck's constant, and it appears all the time when you're doing the mathematics of quantum physics. Notice we now have two expressions for the wavelength of the particle. This means that we can set them equal to each other. For fun, let's solve this for p and see what it tells us. There's an interesting feature about our expression for p. It involves n in it. Remember that n has to be an integer, 1, 2, 3, 4, 5, etc. This means that the particle is only allowed to have very particular momentum when it's in this box. Any momentum the particle has to be one of these. Now you're probably used to thinking about momentum as just being the mass of an object times its speed. Looking at that equation, there's no reason to expect that this kind of effect would occur. Now on the scales that you and I operate in every day, this doesn't really happen. An object can have any amount of momentum that we give it. However, as things get smaller and smaller and smaller, what we think of as just normal everyday behavior starts to break down. And this is just one example. If this is not intuitive to you, don't worry. Quantum mechanics is super non-intuitive, even for people who have been doing it for years. So don't worry if it doesn't make sense to you. But do know that it actually works. Nature does really behave like this. One of the ways we know that it's right is that we're able to use quantum mechanics to build all sorts of wonderful modern conveniences. In fact, I can guarantee you're using one of those modern conveniences right now. If you wanted to build a computer or smartphone or some other smart device from the ground up, you would need to know a little bit of quantum mechanics. So while it may seem weird, and perhaps even a little esoteric, quantum mechanics is absolutely central to the modern world, in a very real sense. As an exercise for yourself, see if you can figure out what this implies about the allowed energies of the particle. I'll give you a little hint to help you out. This is the momentum of a particle. We also know two other things. First is that in general, momentum is equal to mass times velocity. And we also know that kinetic energy is equal to 1/2 mv squared. You should be able to find a way to write kinetic energy in terms of momentum. Once you've done that, just plug in this expression into the equation to figure out what the allowed kinetic energies of this particle are.